All right, welcome to the Unit 1 short overview video. So here we are on the website showing the teacher calendar. Videos right here, student calendar as a starting place if you want to use that with your own website. Here is that overview of the performance expectations and assessment opportunities in Unit 1. This one does not technically have a performance expectation, but we just know students need time on task with the biggest idea in physics. What's even bigger than Newton's laws and conservation of energy, that we can look at a system, we can look at the world, collect data, find patterns, create a mathematical model that acts like some key feature of that system to better understand the system and predict its future behavior. And then of course the science practices. You can see there is 6 assessment opportunities. Those could be a combination of formative and summative, and not all used. Some of these are alternatives to put together a collection of evidence for student understanding. Here is that storyline learning progression. And so we can see our essential question: how do we find and use patterns in nature to predict the future and make data-informed decisions in the present and understand the past? That's our essential question. We use it throughout the whole science sequence. And in this unit, we have 4 major tasks, 4 anchoring experiences with the 4 most common patterns in introductory physics. That's the pendulum experiment, giving us horizontal line; rolling a ball on floor, classic physics experiment, giving us proportional; packing tomatoes, analogous system; marbles, giving us quadratic; and then resizing paragraphs, which I hope to show you totally belongs in the first few weeks of a physics class for inversely proportional. And then a little graphic here that kind of shows once we have these 4 anchoring experiments, for the rest of the year, students can build competency with them. So exposure, practice, mastery. We are in exposure. We want to expose them and give them this foundation, strong foundation with these 4 patterns, but they are not mastering them yet. All right, there is a fun first day activity, or the first day of curriculum for you with the inquiry cube. So here we just saw the whole unit. Now we're going down to a task level, and you can see there's some task narrative and then a bunch of resources. If you went minute by minute, you can then go all the way into the slides. I'm going to show just 2 key slides. This unit is the one that gives us our essential question. And here's just a little picture. It's kind of, it's just a fun storyline. Hey, we found something on Mars, and they study an analogous system here in their classroom. And then after they go through this process, they wild guess at first what's on the bottom, then they collect data, and really it motivates this making better predictions. So they have a guess, then they do an inquiry, they study the cube and take data, then they make sense of the patterns, and there's a lot in there, 8 of them actually. So they don't always catch all of them, but then they talk to each other and learn from each other and then make sense of the pattern. And then they have a data-informed prediction. And of course, that is much better than their wild guess. So they live the experience of the value of evidence-based reasoning, why we do science. All right, so then we have our first experiment where it justifies and gives them the anchoring experience with horizontal line. And I just want to do one peek that we suggest 1 pendulum in the whole classroom, and every student takes data. Some kids are holding the pendulum, some are checking the angle, and then everyone else is taking data because 1, it gives you a chance to control it. Students in small groups take very noisy data and then they can't make sense of it. With you monitoring and every student, we get 2 things. 1, we get a high quality data that they can really make sense of, and 2, it really shows why we have uncertainty in physics. So they are taking the measurement of the same thing, but there is a range in the number. And I will say, you got to take the first data point like 5 times. We got to get this range under a second. And then, so that really makes sense. For middle school, they know you put a dot at the average, but there is some uncertainty in the time. We do not know the exact time. And there was, especially with my small protractor, there is some uncertainty in the angle. I don't know, 5 degrees might be a little big, but large uncertainty bars places the emphasis on understanding the big idea. All right, jumping back, that is horizontal line that introduces the pattern and uncertainty. Then we go into rolling a ball on the floor, classic physics experiment. Just want to show one key slide. that you can show as a teacher to help them through that data discussion. This might be a whole class because it's really the first data discussion, but if they notice that one graph is steeper than the other, okay, that's one point of the triangle, the graph. So what was different in the mathematical model for the ball that came off of a high ramp? Oh, it had the bigger number and it had the steeper slope on the graph. And oh, in the real world, it came off a high ramp. And sometimes students think it is the ramp, but really we took data of the ball on the floor. So what does the ball have? Because it was on the floor because it was on a high ramp. Yes, it is the velocity. All right. There's a lot in here. I want to show that this unit is pretty rigorous. Just want to move that over. We also, all students know that eventually that ball friction is going to roll it down. So if you have some data points and you predict within your range, your confidence is going to be high. If you predict a little bit beyond your range, well, friction's not going to be that much. So you're probably like medium high. But if you have to predict for far away from the ramp, your confidence is dropping. And another consideration is how good. If you were dead on during your data points, well, a prediction within that data range is probably going to be dead on. And so your confidence is high. But if you had scattered or noisy data, well, your prediction, your pattern is going to predict some of that noise. And then we know that after we're ignoring friction with a straight line. So eventually that is going to come up. Or if the ball hits a wall, our model doesn't account for things like that. So your confidence would be extremely low if new physics applies. And we want to teach students to think about that nuance, that not just to predict something with an equation and say that's the answer. They got to be thinking about how confident they are in that answer. All right, and a real fun thing with this one, just like that progression arrow, data informed, let them live the experience. Science works. So half the students go with their wild guess, 5 to 20 feet. The other half go with their data informed, 60 feet. And it's beautiful. You roll the bowling ball, goes right past in the first couple seconds every wild guess. And then it is within an inch of the data informed. That is why we go through the process of science. Data informed predictions outperform wild guesses. There is value in evidence-based reasoning. And there's still yet another piece. This is actually like a week-long lab. There's another one, but going back to that friction. So we want to be candid with students. We want to teach them we use the simplest model that gets to the right answer. We know this from chemistry. It's super obvious with atoms. If you want to talk about why blowing into a balloon expands it or why 2 hydrogen go with oxygen and water, you do not want to use the best model of the atom, the quantum mechanical model. That is too difficult to work with. We want to use Dalton and Bohr. So we want to teach them the nuance. Use the simplest model that gets you the right answer. Warning, this is difficult when you don't know what the right answer is. All right, so all of that gave us the proportional pattern and a few extra along the way. All right, then we have a soft touch with, is this cat going up or down? That is our first CER, and they get support in writing that with the teacher in the packet, but the short video doesn't have time to say much more. Then we go on to packing tomatoes in, and you can follow this. We're going to eventually switch to marbles, but efficiently shipping food from where it's grown to where people eat it has a substantial environmental impact. If you learn to pack things better, you can reduce that carbon footprint. So there is a real phenomenon to follow here. If you go right off with marbles, sometimes students are like, oh, we're just studying marbles. So please use that storyline to the extent that that is meaningful. All right, I just want to show the data discussion, another resource that you could use. Here are some cards right in the teacher calendar. You'll find these, and they will help students. So if you want to switch to smaller groups, so more students are talking, here a student could, you'd have a facilitator at each student group, and that first student asks every student to find a similarity and prepare for a whip around, a rapid fire quick answer. The idea here is we want 5, 10 students talking at a time. Now, eventually, you're probably going to have to pull them back and do a whole class around the sense making. Or maybe you have to go whole class, small group, whole class, small group. But again, we're just trying to get as many students in the role of scientist as we can. The learning really happens in these data discussions if it's well supported. All right, so that gives us our quadratic pattern. Super beautiful. At the end of the day, it's just really obvious that if you double the diameter, that makes it twice as wide and twice as tall. So 4 times, or doubling the diameter quadruples the number of marbles that fit. And what's that pattern when the input doubles, the output quadruples? Quadratic. Nice. Every student who, even if they haven't seen that in their math class, they can get that after that common experience. We do not solve any quadratic equations. All right, so our final paragraph lab is around inversely proportional. And I hope to convince you, even in the short video, that paragraphs are powerful because at the end, everyone goes, oh, I should have got the mathematical model. And so we don't see this again until the forced unit a month later or two. And we want them, when it comes back up, to be able to pull up a piece of paper and for the whole understanding of inversely proportional to tumble back. All right, so the phenomena here is around looking at websites and newspapers, how they oftentimes need to modify text to fit. And there's a storyline of like, how do you convey importance to people and all this other good stuff. All right. What's really cool about this one is this is the most literal walk the triangle. This is so neat. After they measure their paragraphs and they cut them out, if you put the lower left corner of the paragraph at the origin, the upper right is literally the data point on the graph, plotted on one-to-one graph paper that's in the packet. So you can see that if you resize this paragraph, there's something 82 about it all the time. It doesn't matter if it's short and wide or tall and skinny. It always has something 82 about it. All right, excellent. And then of course the little paragraph, which is the same words, but just in smaller font. So eventually they realize, hey, the number is the area. On the graph, the number controls how close the curve gets to the origin. And that just makes sense because it's modeling the paragraphs. Big paragraphs always are going to be far from the origin. Small paragraphs are going to be close to the origin. So it makes sense that small paragraphs have close in curves and will have a small number in their mathematical equation. Then one more step, why is it inversely proportional? And on the short video, not too much time, but I'll just say it's pretty obvious to students that a paper or a paragraph, if you make it twice as wide, if you make the width twice as wide, it has to get twice as short by the laws of nature. That just makes sense to people. If I make it 4 times as wide, it's going to have to get 4 times as short. Whatever I do to the width, the opposite proportional thing is going to happen to the height because there's only a certain amount of paper. And we want to say that many, many ways. And so we got a slide here to remind them. Most important thing said many ways. And that way they can go back and in their data discussion, graphic organizer, and then in their conclusion, they can explain why do paragraphs follow this pattern. All right, so then we, of course, have our in-green poster that stays up the whole year, and we cycle back to it again and again. All right, so the only last piece is we haven't really talked about assessment, and I'm just going to keep it short and show there's a quiz after each of the major labs. And this one has some higher level because it's towards the end of the unit. And we want students to explicitly explain why science we prefer data-informed decisions over wild guesses. So straightforward, but students, that writing process really solidifies that, stays with students. Then starting at question 3 is a very common set of questions that we ask almost throughout the whole year. Can you read a graph in context? Can you reason with it both graphically and with the mathematical model? Can you justify your confidence in a prediction using that model? And then as so often you saw it with the cat, saw it with the in-green cube. Oh, actually we skipped on the in-green cube, but here, which of these is the large font and which of these is the small font? Actually, in the marble lab, I skipped over it, but the steeper curved parabola is actually the smaller marble, and that's kind of neat why that turns out to be that way. But just want to show you that claim, evidence, reasoning spirals throughout. All right, our suggested final summative assessment is if we want students to take what they're learning in class and apply it to their life, well, then they should be getting guidance from the teacher in doing that. And so they should get feedback as well. So that's really an assessment. So let's see how well they're doing it. And to make this manageable, this has a lot of student choice, which is so awesome, but it's also very hard for a teacher to manage it. I'll just say most of the emphasis on the assessment is in this second part, or part 1, playfully brainstorming. They brainstorm their own questions about how to apply what they're learning to their personal life. They apply 3 of them, and then look at how to actually design an investigation. They don't actually have to do it. They just have to think about it. We want some practice, time on task. So later in the course, when they do design experiments, they're getting better at them. All right, and then here's that chance at the community level. They can be looking at social justice, they can be looking at climate justice, passion projects that they have, and this last column scales it up to global context. I will just say one last piece. This is beautiful just to come up with these questions. If you want it really manageable, you want to keep this to a single class period or 2 class periods, strongly suggest that you use this what's going on in here. This was actually made by the New York Times that had a math teacher go and grab graphs from the Times, strip the context, and put them in front of students with some thoughtful wraparound material. So here is 28 graphs about inequality. Here's some ones on teen behaviors. These are high interest, so students can get pulled in, they can get the data, so they don't actually have to spend weeks collecting data. And then all we ask is that they re-visualize. And that's really just to get them thinking about what data visualization is, what you're doing with a graph, so they can either turn it into a pie chart. So here's a tutorial for them to turn it into a pie chart, a bar chart, or get a little more practice with Desmos. And then they, thoughts, wonderings, and conclusions. They just reflect on it. Really great project. That might not always be the right fit, so I'm just going to scroll down and talk as I go. So here's the ball on floor. Just want to show card sort. Also, those discussion prompts I talked about. Again, this one here, I completely skipped this, but 5 layers of support for conclusion writing, a day on really thinking about the big ideas of the unit. And then here is that final assessment. Here's that test with the key and the patterns in your life with examples. Really, we don't want to extend this unit. We want to get to unit 6, climate change and electric guitars. So really try to have people not add a bunch of extensions and try to get students to master every one of those patterns. There's exposure and practice. They should probably master the conclusion because we did 4 back to back to back, and there's a vertical articulation there. That's why we assess that one. But in any case, if honors extensions or there is a time where you need students to go on, so you can work with a small group that needs extra teacher attention for another day. Here's the pinhole camera that has all 4 patterns depending on what question students come up with. All right, with that, that's our brief overview.